Good morning, all. Greetings. This is Dr. P. Ravindra Kumar, lecturer Department College of Engineering, Mechanical Department. So this is my seventh video e-content lecture on numerical problems on heat and work transfer. So far, in the previous classes, we have discussed the basic thermodynamics terminology, basic contents. Next, after then, we have entered into the zeroth law of thermodynamics and its understanding levels. Connected to that one, in the sixth, that is in the fifth video lecture, or 1 to 5th lectures, we have covered the basic concepts. And here, the heat and work transfer calculations, that is what we have learned. Related to that one, now we need to solve some basic problems connected to this heat and work transfer. So here the outcome from this particular content is applying the basic concepts to solve the heat and work transfer from R to the system. Applying the basic concepts, that is what is the how you can make the heat transfer calculation, whether it is heat to be added or heat to be removed. Next one is work to be done by the system or work doing onto the system, that is work supplied to the system or work done by the system. So that particular calculations are going to be done. So applying the basic concepts to solve the heat and work transfer from R to the system. So this is what, when heat is added to the system, it is positive. When heat is rejected from the system, Q is negative. Work done by the system, it is positive. Work doing onto the system, it is negative. So this is the one numerical problem. Here, you just observe the numerical problem there. So the numerical problem that 680 kg of a fish, 680 kg of a fish. So that means the mass of the fish is given. So the mass of the fish is 680 kg, and that fish is existing at 5 degrees centigrade. So here the temperature it is 5 degrees centigrade, are to be frozen. That means you have to remove the heat from 5 degrees centigrade and are to be frozen and stored at minus 12 degrees centigrade. Minus 12 degrees centigrade. So that means here the fish is available to here. So which is at 5 degrees centigrade, right? And it is to be stored at minus 12 degrees centigrade. See, observe this. Minus 12 degree centigrade, minus 12 degree centigrade. And the specific heat of the fish above the freezing point is 3.182, and below the freezing point is 1.717. The freezing point, here observe that the freezing point, so the freezing point it is given as minus 2 degree centigrade. Freezing point is given as minus 2 degree centigrade. And the latent heat of the fusion is 234.5 kilojoule per kg. Latent heat of fusion, observe that one. So in the last class also I have covered the heat can be classified as latent heat of fusion, latent heat of evaporation, latent heat of sublimation. So latent heat of fusion, latent heat of evaporation or vaporization, latent heat of sublimation. So there are three terminologies are connected to the heat point of view. And how much heat must be removed? How much heat must be removed to cool the fish, and what percentage of this one? So that means you have to remove the heat from 5 degrees centigrade to minus 12 degrees centigrade. So there are certain things are there. That is, one is the above freezing point. So this is above freezing point, and this is below freezing point. Below freezing point. right? And we all know that most of the times we use to apply Q is equal to mc delta T, right? So in this case, heat to be removed. That's why here it is mCp, the initial temperature minus the final temperature. Initial temperature minus the final temperature. Initial temperature minus final temperature. So when you do this one, heat to be removed. Heat to be removed above the freezing point. What is that? So mass is 680 kg and fish above the freezing point. So above the freezing point. So first thing is you have to calculate this one. Above the freezing point, it is 3.182 above the freezing point, and initial temperature is 5 degrees centigrade. So from 5 degrees centigrade to final temperature, that is minus. So that is minus of minus 2 degrees centigrade. Then you will get it as 15.146 megajoule. So this much amount of heat to be removed above the freezing point. Next, there is a heat to be removed, latent heat. So now the next thing is the latent heat is going to become. So that is the latent heat of fusion of ice, it is given. Latent heat of fusion of ice is 234, right? So the latent heat of, this is the sensible heat where I can call it, this one is the sensible heat. And the latent heat, so the latent heat is nothing but equal to m into h of g. Latent sensible heat is equal to Q is equal to mCp delta T. Latent heat is equal to m into h of g. That is the evaporation, latent heat of fusion. So this is this h of g here. You can consider it as a h of g, latent heat of fusion. And here this is also the h of g, latent heat of evaporation. This is also h of g, latent heat of sublimation. So that particular things you have to add. So the mass of the fish is 680 kg and the latent heat of fusion is 234.5. So you will get this one. Next one is heat to be removed below the freezing point. So here this is the below the freezing point. So the below the freezing point where you have to start 680 kg and this is below the freezing point, below the freezing point, specific heat below the freezing point into T1 minus T2, that is the minus 2 minus of minus 12. So you will get 11.676 megajoule. So what is that total heat that, if you add this one, so this is, in this case, this is Q1, this is the Q2, this is the Q3, total heat. That total heat is nothing but you will get as 159 plus 15 plus 11. So it is totally around 186.28 megajoule. But here it is asked what is the percentage of the latent heat. So that percentage of the latent heat is nothing but, here this is the latent heat. So this latent heat, it is 159.46, 159.46 divided by, or into 100 divided by total heat. Total heat, it is 180 because the percentage is mentioned. So in this case 159.46 into 100 divided by 186 divided by 186.286, this is the total heat, is equal to 85.6 percentage. So that is the percentage of the latent heat. What is the latent heat percentage? So that means what you have to understand is that what is the amount of heat, what is the amount of heat which is removed in the sensible part side and in the latent heat part side. So this is how you have to solve the numerical problem. So always we know that Q is equal to mCp delta T, that you should not forget. mCp delta T, and based on that one, whether heat is to be added or heat is to be removed, what kind of heat it is, that is whether it is latent heat of sublimation or latent heat of fusion or latent heat of evaporation. Connected to that one, you have to apply the, you have to solve the numerical problem. So this is in the previous class we have discussed the heat and work transfer connection. So on that aspect, this is the first problem. And the second problem here. The second problem, it is a milk chilling unit. It is a milk chilling unit can remove the heat. Milk chilling unit. So milk industries. So in milk industries, what is going to do that part? So milk chilling unit can remove the heat from the milk at the rate of, see, megajoule per hour. Time is also mentioned here. Hour. 41.87 megajoule per hour. Heat leaks into the milk. This can remove the heat from the milk at the rate of this one. Heat leaks into the milk from the surrounding. Heat leaks into the milk. That means the heat is going to enter into the milk from the surrounding at an average rate of 4.187 megajoule per hour. Find the time required. Here, how much time required for cooling a batch of 500 kg of the milk from 45 degrees centigrade to 5 degrees centigrade. Take the specific heat of the milk to be 5.1 4.187 kilojoule per kg Kelvin. So, and we all know that this is the Q is equal to, where this S is nothing but the specific heat, and you can also consider it as a MCP delta T, right? So, M is nothing but 500 kg of a milk, and the specific heat of the milk, it is also mentioned 4.187 kilojoule per kg Kelvin into temperature. So change in temperature. What is that change in temperature? That is, you have to remove the heat from 45 degrees centigrade to 5 degrees centigrade. Removing the heat from 45 degrees centigrade to 45 degrees centigrade to 5 degrees centigrade. So you will get the 83.74 megajoule. What is the net heat removal? Here the heat is entering. The net heat removal means Q is equal to, we may write it as Q1 minus Q2. That is nothing but equal to here. Heat can remove, that is the heat rejected. So this heat rejected minus heat leak. Heat rejected minus heat leaks into the milk. So what is the heat rejected? What is the heat? This can remove the heat from the milk. What is that? It is 41.87 minus. See this one. This is minus 4.187. 4.187. So you will get it as 37.68 megajoule per hour. Megajoule per hour. Now, how you are going to get that particular time? So time which is in minutes or in seconds or in hours. So here there is a megajoule is there. So that it is 83.74 megajoule by, here this is 30 megajoule per hour. So the net heat removal, that is 37.68 megajoule per hour. So when you do this calculation, megajoule getting cancelled, finally you will get the hour. So what is that hour? That hours is 2 hours. It is going to take 13 minutes, 2 hours, 13 minutes, 20 seconds, 20 seconds, right? So this much amount of a time is required in order to complete this particular task. So this is how you have to solve the numerical problem related to the heat point of view. So the standard formula is Q is equal to MCP delta T. But how tricky that particular Q is equal to MCP delta T is going to play to solve this particular numerical problems, that is what everyone has to understand. Everyone has to understand whether the time is required, how much time is required, or how much work is required or how much heat is required. So all that particular tasks is going to be done. Next, so there is another problem that it is desired to. The third problem is it is if it is desired to melt aluminum, if it is desired to melt aluminum with a solid state specific heat 0.9 kilojoule per kg, latent heat is 390 kilojoule per kg, atomic weight of the aluminum is 27, density in molten state is 2400 kg per meter cubed, and final temperature is 700 degrees centigrade. Find out how much metal can be melted. Find out how much metal can be melted per hour with the above kilowatt rating. With the above kilowatt rating. Other data are as in the example in such a way that also find the mass of the aluminum that the above furnace will hold. The melting point of the aluminum is 660 degrees centigrade. Melting point of the aluminum is 660 degree centigrade. So now how you are going to carry out this particular problem? So the heat required to melt this particular problems. So how you can solve this particular problems? So the heat required per kg of aluminum. So you just observe heat required per kg of aluminum. So we all know that this Q is equal to mCp delta T, but here it is per kg is mentioned. So that is Q per kg. Q is equal to, now you will get Cp delta T. So what is this specific heat? It is 0.9, from where that is the melting point of the aluminum is 660. So it has to start at 660. And what is the temperature? That is it has to that 15 degrees centigrade is the final one. 660 to 15 degrees centigrade. 660 to 15 degrees centigrade. Initial minus final. Plus 390 is nothing but the latent heat. This is nothing but the latent heat. Next, what is the here? There is a 29.93 divided by 27. This 29.20 the atomic weight is given as a 27. Atomic weight is given as a 27. So that the mass here, you have to calculate the mass here. So that mass is the aluminum which is to be existed from the solid state and also the liquid state, here 29.93 is the atomic weight divided by the 27. So that is 29.93 divided by, that is 29.93 atomic weight per atomic weight, 29.93 per atomic weight. And what is that atomic weight? Atomic weight is 27, right? So this is 29.93 per atomic weight. This is what you have to observe. So you should have to be more careful about this particular point. 29.93 per atomic weight. That means the atomic weight is given as 27. So here you have to be more careful. Into temperature, that is from 700 minus 660. then you can get the answer, that is 1014.8 kilojoule. So you will get this particular problem from the PKNAG textbook, right? So you can observe this particular problem from the PKNAG textbook, and it is the solved problem, which is the connection of the 3.7 and 3.8. So there are two problems are connected. So 3.7 and 3.8. So this is the link is there. The link between 3.7 and 3.8, the aluminum problem, that is the melting of the aluminum. So melting of the aluminum means there are the liquid states are there and solid states are there. So the heat to be removed. So it is 1014.7, and this is here the efficiency is mentioned. 70% efficiency is there. This is efficiency. Heat to be supplied. It is here. It is given as a, if an electric furnace has 70% efficiency. If an electric furnace has 70% efficiency, that means this much amount of heat divided by 0.7, you will get this particular 1449.7, right? So, but with the given power, the rate at which aluminum can be melted, what is that particular aluminum melting point? So, the aluminum, it is 217. So here with the given power, the rate at which aluminum can be melted is so you can find out from this particular formula, that is Q is equal to here, the Q is equal to that value, you will get it as initially it is given as to melt 5 tons per hour. So 5 tons per hour means 5 into 10 power 3 kg, 5 into 10 power 3 kg, and the total heat removal. So it is around 10, it is around 1094.5, 1094.5 divided by the furnace efficiency, it is 0.7%. So you will get this particular value as 217, 217 into 10 cubed, 217 into 10 cubed kilowatt. So that you have to apply here. 217 into 10 cubed into 3600 divided by that 14 point, this one, heat to be supplied, 1449.73. 14.73, you can get in kilojoule power, it is 5.39 tons per hour. So what is the mass of the aluminum that can be held in the above furnace? So that is nothing but equal to, it is around 2.18. That is this 2.18 is nothing but the volume. So you can get that particular volume. So that is here the volume which you are going to be calculated as 3 into 5 power the volume which you will get, it is 3 into 5 tons divided by 6,900, 6,900. The density of the, this is the density of the aluminum, 6,900 is the density of the aluminum. So you will get the volume, and volume into 2,400 kg, then you can get it as a 5.23 tons. So this is how you have to solve this particular numerical problem. So here there is no new formula is used except only Q is equal to mCp delta T. But in this particular regard, then what is the basic fundamentals that you can apply to solve this numerical problem? So it is especially this particular problem is the connection of two problems in PK textbook. And here the what you have to understand is that so when you use the Q is equal to mCp delta T, mCp delta T, Q is equal to mCp delta T, or this Q is nothing but equal to this is the sensible heat. This is the sensible heat, and this is nothing but the latent heat. This is nothing but the latent heat. And in this particular aspect, how we are going to solve this particular mass of the substance? So that we all know that density is equal to mass by volume. So you see the basic fundamentals you have to mass by volume. Density is equal to mass by volume. That is kg per meter cube density. And the specific volume is nothing but the reciprocal of the density. So this is how you have to get the ideas in your mind to solve this particular numerical problem. Right? So all the things are how well you are going to acquire the basic fundamentals to solve the numerical problem. Next, there is another problem is there, that is here heat is required to melt 5 tons per hour of iron from a charge. So this is also from the yes. So this particular problem is the connection between the one after solving this particular after solving this particular problem, then you can easily solve this particular three problems. After solving this particular problem, after solving this particular problem, then you can easily solve this particular case. So that is the connection here. So all the things are here, nothing is there. That is what you have to observe is that heat, finally, heat required to melt 1 kg of iron at 15 degrees centigrade to molten metal at 1650 degrees centigrade. In this transformation, the heat required to raise the temperature from 15 to 1535 plus latent heat plus heat required to raise the temperature from 1535 to 1650. So in all the fundamentals, Q is equal to mCp delta T, Q is equal to m into HFG. So this latent heat is nothing but this particular 270. So that is the 270 here. The latent heat is given as a 270 kilojoule per kg. So that you have to use. And finally, related to that one, once if you obtain the Q value and the melting rate, so the rate of heat supply, see here, 5 into 10 cubed kg per hour into 1094.5 kilojoule per hour. Since the efficiency has the 70%, the rating of the furnace would be calculated as the rate of the heat supply per second. So the furnace efficiency is given as the 70%. So you can solve, and finally the find the dimensions of the cylindrical furnace. If length to diameter ratio, that is L by D ratio is given, it is given as a 2. So that you can easily solve this particular problem. Right? So it is the connection between the fourth problem and the third problem in this particular PowerPoint presentation, that everyone has to understand this particular connection. Next, there is a piston. Now, heat transfer problems are over. Now, the time for work transfer calculation. So, the time for work transfer calculations here. What is that? A piston and cylinder machine containing a fluid piston and cylinder. So, this is the piston that is in a system. This is the piston, right? And this is the cylinder, piston cylinder. So this is the piston, that is P, cylinder, containing a fluid system has a stirring device. This is the stirrer. This is the stirrer. In the cylinder, the piston is frictionless, so no friction is there, and it is held down against the fluid due to the atmospheric pressure of 101. So the atmospheric pressure is given as 101.32 kilopascal. The stirring device is termed 10,000 revolutions. So here N is given. It is going to revolute 10,000 revolutions with an average torque against the fluid air. So the torque is given. The torque is 1.275 meter Newton. Meanwhile, the piston of 0.6 diameter. So this is the piston diameter is given here. The piston diameter is given as a 0.8 meter piston diameter. Find the network transfer for the system. Find the network transfer for the system. So when you rise up and down, this weight, so what is going to happen with this particular pulley? This is going to make some revolution. And once the stirring action is occurring here, then there will be the change in the fluid properties. There will be the change in the fluid properties. So how you are going to calculate for this particular thing? So first thing is work done by the stirring device. Work done by the stirring device. So the work done by the stirring device. So that work here already we have covered that work is nothing but equal to 2 pi nt divided by 60. 2 pi nt divided by 60. 60, sometimes the power, the things what you have to observe, whether you are calculating it is in kilojoule or it is kilojoule per second, that is in watts, right? So the most of the time, so power is in watts and this work is in kilojoule. If you do by 60, then you will get in power. So that means you have to apply the 2 pi nt. So 2 pi, what is the number of revolutions? It is 10,000. And what about the torque? The torque is 1.275. 1.275. So you will get the work that is W1, that is work done by the stirring device upon the system. First thing is you have to do the work onto the system. So you will get the work for this particular case is 80 kilojoules. So this is 80 kilojoules. Next, the second thing is here the work done by the system upon the surroundings. That means the piston is going to move in this side. Once the fluid gets expanded, the piston is going to move from the inner dead center position to the outer dead center position. So there is another work is going to be getting. So first thing is when you give the work input to this one, so that the fluid gets expanded, and the expanded fluid is going to turn the work towards the surroundings. So the piston is going to move towards the right direction. So that W2 is equal to here. There is another formula is there. So already we know that the work is equal to PdV work. Work is equal to PdV, right? So work is equal to PdV. That and here that pressure is Newton per meter square. This P is nothing but the pressure, Newton per meter square. Newton per meter square. So if you do that, there is a force. What is that particular the atmospheric pressure of 101.32 kilopascal. So this is the atmospheric pressure. That is here you can also consider it as a P into P, and this dV, that is the volume, where that volume is area into length. That volume is area into length, right? So this is the change in volume, dV. So here this is all the total area, and the piston is going to displace 0.3 meters. Piston is going to displace 0.3 meters. So that W2 is equal to, and what is the atmospheric pressure? This is the atmospheric pressure. It is 101.32 kilopascal into area. that is pi by 4 d square area of the cylinder, pi by 4 d square into L, that is this displacement, the piston displacement. So it is 0.3. So the diameter is 0.8 square, and this is 0.3 meter. Then if you solve this particular case, then you will get here as a 22.9 kilojoule, 22.9 kilojoule. So finally that total work is nothing but equal to W1 plus W2. So this is the W1 is 80 kilojoule and W2 is nothing but 22 kilojoule. So the total work which you are going to be getting is the total work is uh, because in this case when you talk about the work, here you are giving the work input. So you are giving the work input. So that means work input means this is the work doing onto the system. So it is minus sign. Work doing onto the minus sign. So what is that here? That W is nothing but equal to, first this is the minus 80 kilojoule. This is minus 80 kilojoule. Why? Work giving to the system, work doing onto the system, it is minus 80 kilojoule plus the work done by the system. Here the piston is going to work done by the system, it is 22.9. So finally that you will get as a minus 57.1 kilojoule. So that minus sign is going to indicate that you have work doing onto the system, So this is how the work transfer calculations that you have to do in this particular site. So the applying the basic fundamentals, whatever the basic fundamentals we have listened in the previous lectures, then applying that particular basic fundamentals to solve the numerical problems of heat and work transfer calculations. Heat and work transfer calculation. So this is the work transfer calculation, that is the PDV work. So that basic fundamentals, how you have applied that basic fundamental. So this is the answer, minus 57.1 kilojoule. Next, there is another problem is also there. So in this particular problem, a closed cylinder which is of a 0.25 meter diameter, 0.25 meter diameter is fitted with a light frictionless piston. The piston is retained in position by a catch in the cylinder wall, and the volume on one side of the piston contains air at a pressure of 750 kilonewton per meter square. The volume on the other side of the piston is evacuated. Volume on the other side of the piston is evacuated. A helical spring is mounted coaxially with the cylinder in this evacuated space. See here, evacuated space, to give a force of 120 Newton on the piston in this position. The catch is released. And the piston travels along the cylinder until it comes to rest after a stroke of, see here. Now when it comes up to this particular position, it is going to come to the rest. Stroke of 1.2 meter. The piston is then held in its position of a maximum travel by a ratchet mechanism. The spring force increases linearly with the piston displacement to the final value of 5 kilonewton. Calculate the work done by the compressed air on the piston. Calculate the final air on the compressed piston. So here you have to make the calculations as in such a way that first of all you have to calculate the mean force. You have to calculate the mean force. So that mean force you will get as the what are that here there is a force that is 120 plus 5000, right? So 5000 here, this one. So a final value it is. So from this position to this position, so the mean force is this one. So once you will get the mean force, it is 2560 Newton. It is Newton. Then what is the travel? That is the displacement. That is from the position, initial position x1 to the final position x2. It is 1.2. So the travel, or the, I can say it as a displacement. So the displacement, it is equal to 1.2 meters displacement, right? Next one is work done here. What is the work done? That work done is equal to the mean force. So mean force into change in displacement, that is the ds. See here, ds is equal to l is, that is 1.2. So it is 2.2560 into 1.2. So what you will get? You will get in a Newton meter, that is 3.072 kilojoule. So that is here already you know that this is a Newton. The units Newton meter is nothing but joule. So if you put the answer in a kilojoule, that is 3.072 kilojoule you will get. Next, there is the formula, and we all know that the force. So this particular force here, this is the spring force. So that spring force is nothing but equal to the initial it is around 120 plus kx. K is nothing but the spring stiffness. K is nothing but spring stiffness, that is Newton per meter or kilonewton per meter. This is always observe this one. This is the Newton per meter, and already it is in newtons, and Newton per meter. And what is that particular movement here? This is 1.2 meter. So it is x 120 plus k into x, that is this is also meter. So meter cancelling, Newton, and to the left side it is also Newton. So from this case, where you can get the spring stiffness, right? So that spring here, this particular force is given as a 5000. So this is 5000 is equal to 120 plus k, that is what you have to find. X is 1.2. So you will get the k value as a spring stiffness value. You will get that spring stiffness value as a 4067. 4067. It is Newton per meter. 4067 Newton per meter. Once you get the spring stiffness, then you have to make the calculation. That is the Fxd. Work is equal to, we all know that work is equal to integral of the lower limit, that is 0. The upper limit is displacement is 1.2, right? So this from this position to this position 1.2, and Fx dx. Fx dx. What is this Fx dx? So that Fx is nothing but equal to 120 plus k value is 4067 into 1.2. So when you solve this particular case, you will get the work done as so you can get the work done from this particular case is 3 let me 3.072 3.072 kilojoule. So this is the answer. This is the answer. So this is how the work transfer calculations that you have to carry out. So whatever the basis, that is whether you are doing the shaft work or work doing in stretching the surface film, or work doing in stretching the wire, or paddle wheel work, or magnetic work, or you are doing the electrical work. So all that particular basic fundamentals and spring stiffness formula, that is the work done in spring stiffness, that also you should have to observe. So the work that is W is equal to half k x square. So x is nothing but k is nothing but the spring stiffness. K is nothing but spring stiffness. So sometimes this particular formulas also you have to use, right? So this is one problem. So there is another problem that is here. This is also connected to the work point of view. So a steam turbine drives a ship's propeller. Steam turbine drives a ship's propeller through an 8:1 reduction gear. See how the mechanical problems are connected to the realistic situation. The average resisting torque imposed by the water on propeller is 750 into 10 cubed meter Newton. That is the torque. And the shaft power delivered by the turbine to the reduction gear is shaft power is given 15 megawatt. The turbine speed is 1450 rpm. Determine the torque developed by the turbine. See here. And we all know that the power is equal to, there is a power is equal to torque into omega. So this is nothing but 2 pi n into t divided by 60, right? So here it is asked to find out the torque. So they have asked the torque. Torque is equal to power by omega. What is the power? That power is given as a 15 megawatt. So this is 15 megawatt. Convert that into kilowatt, right? Divided by omega. That is 2 pi. What about the n? 2 pi n. N number of revolutions it is 1450. 1450 divided by 60 revolutions per minute. Revolutions per minute you can get. So that particular task, the torque which you are going to be getting as 98.84 kilometer Newton. Kilometer Newton, 98.4. So this is the answer. And once this is known, then the second thing is the power delivered to the propeller shaft. The power delivered to the propeller shaft. So that is also power is equal to torque into omega. So what is here? The imposed by the water propeller. So when it comes onto the propeller, the torque is given. So that particular torque is 750 into 10 cubed and omega 2 pi nt divided by 60. So the speed is same. The propeller speed is 1450 and you can get the power output. The third one, the net rate of working of the reduction gear. The net rate of working of the reduction gear. So what is that here? Once the power developed by the propeller shaft, it is 14.23, but the net rate is the turbine. The shaft power delivered by the turbine to the reduction gear is 15 megawatt. 15 minus 14.2, you will get 0.7647 megawatt. So this is how the uh, connection between the power, work, torque, right? So this particular problem comes under to the shaft work or the shaft power. So in the fifth video lecture, we have discussed the basic fundamental connected to that particular thing. Next one is last one. So this is also the very easy problem. So here also what is the work done? A fluid contained in a horizontal cylinder fitted with a frictionless leak-proof piston is continuously agitated by means of stirrer passing through the cylinder cover. The cylinder diameter is 0.40 meter. During the stirring process lasting 10 minutes, the piston slowly moves out. See here, the piston slowly moves out. Piston slowly moves out 0.485 meters against the atmosphere. The net work done by the fluid during the process is 2 kilojoules. The speed of the electric motor driving the stirrer is 840 RPM. Determine the torque in the shaft and power output of the motor. Determine the torque in the shaft. So we all know that torque is equal to power by omega. What is that particular power? How you are going to that particular power? So first thing is you have to get it from the basic fundamentals. So that basic fundamentals. So in this case, what is the change in volume? The change in volume is area into length. And here already the data is given. The diameter of the cylinder is mentioned. So pi by 4 d square into L. So you will get the change in volume. So as the piston moves against the constant atmospheric pressure, so this is the piston is going to move in the right direction. The work done is P into delta V. And we all know that the atmospheric pressure is 101 kilopascal and the change in volume is 0.01, 0.061. So here you will get apply. So finally you will get the work transfer. But what about the net work done by the fluid is 2 kilojoules and net work done by the motor is 4 point. That means the total work here piston is going to move 6.175 minus 2 kilojoules. You will get the net work done by the motor is 4.174. So therefore power of the motor is this is 4.175 divided by omega. So that omega, how many revolutions are there? So it is going the time work done divided by the time that it is lasting for 10 minutes. So it is going to last for the 10 minutes. So the formula you should be careful that the power is equal to T omega. Power is equal to T omega. Torque is equal to power divided by omega or work divided. So the work divided by time, you will get it as the power divided by omega. So you should be careful about this particular case. What is the power? So the net work done here, the total, because in this case, what is going to be happening when you are doing the work onto this system, the piston is going to move from the left direction to the right direction. So for this particular case, the piston moves against the atmospheric pressure. So that is 6.175 net work done by the fluid. So this is the net work done by the fluid. It is 2 kilojoules. So 6.175 minus 2 kilojoule, you will get the net work. It is 4.175 net work kilojoule. Observe this. This is kilojoule. And this is going to lasting for the 10 minutes. So it is 10 into 60. You will get it as in terms of the watts. So the torque on the shaft, torque is equal to, now the power, it is 6.96 divided by omega. Omega, it is again 2 pi nt divided by, that is a 2 pi n. Omega is equal to, right, 2 pi. What about the number of revolutions of this particular shaft? It is 840. So it is 840 divided by 60. 2 pi n divided by 60. And here, if you substitute this one, then you will get the torque as 0.0791. So this is how you have to make the calculations connected to the heat and work transfer. So this completes the all problems. So thank you. Hope you have received the heat and work transfer calculation.